What happens when you measure a quantum qubit? Imagine holding a tiny spinning coin that can be both heads and tails at the same time. That's similar to what a qubit does before you look at it. When you measure a quantum qubit, it's like peeking at that coin. The superposition, or the blend of both states, suddenly collapses into one definite state. Before measurement, a qubit exists as a mix of two possibilities, described by complex numbers called amplitudes. These amplitudes tell us the chance of finding the qubit in either state, 0 or 1. When you measure, the qubit randomly chooses to become either 0 or 1, based on those probabilities. If the amplitude squared for 0 is higher, it's more likely to end up as 0. If the amplitude squared for 1 is higher, then 1 is more likely. Once you measure, the superposition disappears instantly, and the qubit behaves like a regular classical bit. This collapse is permanent. The original quantum information stored in the amplitudes is lost. The process is inherently probabilistic, meaning you can't predict the exact outcome every time, only the likelihood. If you measure the same qubit again immediately, you'll get the same result because it's now in a definite state. Measurement can happen at different times during a quantum process. Sometimes it's at the end to read out the final answer. Other times, it's during the process to decide what to do next. Partial measurement involves checking only some qubits, which helps in correcting errors without destroying the entire quantum state. Mathematically, measurement is described by operators that project the qubit onto one of the basis states, like 0 or 1. After measurement, if you measure again in the same basis, you'll get the same result, confirming the qubit is now in a classical state. From a quantum information point of view, measurement is how quantum data becomes usable in the real world. It turns the quantum superposition into a classical bit that can be used for further calculations or communication. Different physical systems like superconducting circuits, trapped ions, or photons use various measurement techniques, but all share the goal of collapsing the quantum state into a classical outcome. Advanced methods like Bell state measurements are used to handle entangled qubits, which are key for quantum teleportation and secure communication. So, in simple terms, measuring a qubit is like peeking into a mysterious world and forcing it to choose a single reality. It's the bridge that connects the strange quantum realm to the everyday world of classical information.